Hello, boys and girls. Welcome to another episode of FoulkesBrau. Today is Tuesday, the 31st of March. Is day 5 of lockdown in South Africa. Last night we were addressed by our president. No surprises there. As of last night, we have 1,326 infections in South Africa. That's it then. But what they've also pretty much insinuated is that they haven't been testing that many. So we really don't know what the infection rate is. The important thing is that they're going to ramp up testing. Currently, they've enlisted 10,000 volunteers or staff to go around in the rural areas and or in cities, whatever, however you want to take it, to start testing people. That's all well and done. Problem is that we don't really know what the real infection rate is. Apparently, we've had now 3 fatalities with this thing. Yeah, just sad. If I look at what's happening in the rest of the world, how quickly people are getting infected. For example, in the city, if you look at infection rate and you look at the ratio of death to infection, it's roughly about 10%, and that sort of correlates everywhere else. And all very sad if you think about it. We're going to carry on with part 2 of our PLC programming and design background video or project that I'm busy working with. I just want to draw your attention to a few things. You go here, we'll bring paint up. I just want to just to show you how OBs work. Oh, here we can put text here. We've got OB1, right, by drawing. Okay, we've got OB1. Now, what happens? OB1 scans like this. At this point, let's say somebody unplugs module. So we'll get a module OB, for example, and this will scan whatever code that you have written in there. If anything, you wrote any special code, maybe you wanted some data logging, special stuff, you wanted to send an email. If you set your PLC up as that, OB1 will go to this module interrupt or module OB, scan whatever code you've done, and then it will come back to OB1 and continue scanning. If we have OB1, we have in our case, we have OB1, very good with paint. And then we have OB33, our cyclic OB. Then we have same scenario. We have our module OB. What would happen? OB1 would start whatever code is in there, it doesn't matter, but because we've got this cyclic interrupt 500 milliseconds, it will jump into OB33 and scan our code. Under all circumstances, everything being normal, there's no module fault. When OB33 is done, it goes back to OB1, continues. Let's say we have our error, bang, goes to the module OB, comes back when it's done there to OB33, finishes scanning what's there, then goes back and repeats whatever in OB1. But because we don't normally put anything except block calls or whatever, special things in there, there's nothing that's going to scan in OB. But we'll call OB1, jump straight to OB33, process OB33 under normal circumstances, go back to OB1, and then start OB1. If we have a module interrupt or whatever, jump out of whatever we're doing, go to the module OB or whatever error OB, and when it's done there, jump back, continue where it left off processing our normal cyclic OB. Other thing I just want to draw your attention to, I did make a bit of a balls up of write code every day. We still use our geo to log, let's get take the geographical address and get the logical address for it. There's only one thing that I forgot to mention. So what we're doing is we're loading the logical address here. We put it into address register 1. In other words, whatever this thing is returned and put up here, we want to go and get the actual physical value of the first, well, the word. We want to get the first word of there. You remember from our hardware config, if we go and look here, network view, valve. So what we're saying is return that first word. So it's whatever's contained here in that slot, we are going to get input word basically 0. And we're going to just store it in a scratch pad, local word 0, like a temp variable that I don't have to use. It's not going to be valid at the end of this thing. Then I call this dp read data function, which we have to use with Siemens if your data is consecutively. In other words, if I have 3 or more bytes of data that I want to read, not 4. 3 or more, but not 4. 3, then from 5 up to whatever. Return value stays our error. And then the record, all I've done is I've put a pointer to data instance bit 12. This is dangerous. So if we change the block interface, we add more parameters here, that data instance bit 12 is going to move on. But unfortunately, block works like that. So I actually have to tell it, put a pointer to there, that's 12. I want 34 bytes. Now, how much? You're going to see now where that's going to be a problem. So you just need, what I will do, put a comment in, remember to change after segregation. Okay. So we bring our Adobe up. This is the bit breakdown for Alma valves if you're using Profinet. Profibus will have a similar document. Modbus, if you use that rubbish, will have a similar document. What is important, we have to read the description of the data interface. Configuration of cyclic data transfer is done via the Profinet controller only. In other words, the PLC is the master. Selection of the input channel or the respective input and or output date is performed via the slot sub-slot configuration used to program the Profinet controller. All I/O data is provided in slot 1, sub-slot 1. So yesterday I told you PIA, switching around. If we go, we look at our call for this block, 33, Remember, we said it's slot 1, subslot 1. Well, now you know why, because in the manual it tells you IO data is provided in slot 1, subslot 1. Data is structured in various blocks with different properties. The following section comprises the explanation of processing basis described on the basis of the automation system. Input data is sent by the field device to the automation device. Logical. Output data is sent by the automation device to the. In other words, input data is stuff we want to read from the instrument. We want to know its status. Is it open? Is it closed? Whatever it can give us. Output data is if we want to control it. We want to tell it open, close, start, stop, depending on the device. Okay. Blah, de, blah, blah, blah. And they go and explain a whole lot about gray bits and whatever. I don't like that. How they put the. But to their credit, they've actually given us a table. So they tell us byte 1 is the logic signal. I wish they'd actually. They start with byte 1. We always start with byte 0. We have to keep that in mind. The byte 1 logic signal, 3, 6, and 7 are collective signals. Other 4 the logical byte indicator, blah, blah, blah. That is set when the actuators receive the command, perform an operation, or whatever. So if we look at byte 1, end position open, the limit switch operate in direction open for Fulk seating, Fulk switch, and limit switch operation. Blah, 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 blah. There is no signal. Byte bit 1, limit seating. At least this time they get that right. Bit 0, bit 1. Why couldn't they get fucking byte 0 right? Limit seating, blah, blah, is closed. 2, set point reached. 3, not ready, out. Collector signal 4. This junction, all bits comprised of 14, not ready, remote, run. The actuator cannot be operated from. That might be important. We'd like to know if it's open. We'd like to know if it's closed. Set point reached. Well, we're not using a modulating dial, so we care about that. Not ready remote. We'd like to know if we can't drive it from the PLC. Remote means the PLC is controlled. Local means they're operating it in the field. So we'd like to know if it's not running open. Okay, so we've given it a command. It's traveling to the open position. Running close, we've given it a command. Drive closed position. Warning. Yes, we'd definitely like to know if this thing has got a warning. No. Fault. We'd definitely like to know if it's got a fault. Byte 2 actuator signal. Byte 1 called logical signals. Byte 2 actuator signals. Thermal fault. We'd like to know. Phase fault. There's a 3-phase motorized actuator, so I'd like to know if there's a phase failure. Fault with a phase. We'd like to know if the selector switch is remote, definitely, or if they switched this thing locally on the motor to remote or to local, we'd like to know that. Okay, here we go. We actually want the limit switch, so end position for limit seating. I don't particularly care for limit seating. What do they mean? Fulk seating, Fulk switch and limit switch off. For limit seat, looks like a duplicate. For limit, because we would work with limits. For limit seating, valve has traveled to its limit and it's actually reached the limit in the direction open. Okay. I can see where you would use it. So you have to have given it open command and it's made the limit. This other one doesn't care You gave it an open command. It's the actual physical position. I would rather use this. The other one we would use for travel fault. We've given it use it maybe a time. We gave it an open command. And now we wait. Does it reach that bit? And if it doesn't reach it within a certain amount of time, we know it's taken too long to get there. But these are the actual physical limits. Okay. We want definitely byte 1, byte 2. Bytes 3 and 4, if a position transmitted potentiometer pulled in the actuator, bytes 3 and 4 used to transmit the current actuator position. Well, I didn't, not modulating valve, so I didn't install position back in the valve. I don't care about position. I care that the valve is open, either going to be fully open, fully closed. That's all I care about. I don't care about where it is in the greater scheme of things, because I've got the limits for that. Okay, byte 5, device status. Not ready for remote. The actuator cannot be operated from. Okay, we like that. Warnings again. Okay, we have to remember it's byte 17 and 20. 17. Warning fault. Maintenance required. Okay. Out of spec. Actuators operated outside the normal operating conditions. And we'll have to look at what that is. Function check. Actuators being worked on. Failure. Actuator function. Device okay. I'd like to know about device okay. Not much we want in. I have to put the whole lot and I'll show you why. Byte 6 operation status. Operation pause active. And so, because it's a motorized valve and we're using it on and off, and this is 3-phase 505 volts driving this thing. So you're going to tell it to open, bang, and now you're going to have a pause time, whatever we decide to set up in the valve, before you can reverse it the other way. So it's to prevent you from driving the valve and then, oh, it's going that way now, let's just switch it that way. You don't want to be doing that with a phase motor. Okay, in intermediate position, not in open or closed. Start stepping mode, MPLP. Don't actually. E position. Oh, idea. Actuator is running. Drive is moving. Operations hand wheel. Output drive rotates without electric harness. In other words, they opening with a hand wheel. As the running in remote. Or running in local. I'm not sure if I care about that. Well, we'll see. Intermediate positions, we don't care about. So what we can define is 8 positions across from fully closed to fully open. I actually don't care about that. I care about it's open or it's closed. Discrete inputs, because we've got digital ins on the valve. I'm not wiring anything. Everything we're doing is via the bus. I don't actually care about the discrete inputs. Byte 13, not ready remote 1. Wrong command. They said we give it the wrong thing via the Profibus. Click to switch not remote. Interlock active. Not interlocking the actuator in hardwire. We're doing it all via the PLC. Push stop button. Emergency stop, we're not wiring that into it. Emergency behavior active, I don't care about that. Failsafe field bus. IO interface, no. We care about any not ready remote. Not ready remote 2, failsafe unit, blah blah blah, still function. We're not putting any safety integrated level into this. Don't require it. Enabled interlock bypass, EST, valve stroke test, service active, and wheel active. No. Okay, fault signals. Byte theme, configuration error, main quality. Due to insufficient mains quality. Faults cannot detect the phase seat. Okay. In the preset. Okay. So, might want these faults. So what this could mean is that voltage is too low, it's under voltage. On below a certain threshold of 525 plus 15 minus 25 or something. Remember the exact well, doesn't matter. What it does matter is voltage is too low or too high, it's out of that whatever this thing's tolerance is, then we're not going to get it can tell us mains quality. And that's internal fault. Now, protection tripped. Okay, phase fault. When connecting to 3-phase AC system, internal 24-volt DC supply of the phase 2. Connecting to 3-phase or 1-phase AC with external. This is just telling us we will have 3-phase with internal 24-volt supply. It's just telling us phase. Torque fault, direction open. Yes, we'd like that. Torque fault close. Internal error, we'd like that. Warning, no reaction. Okay, actuator reaction to operation. Okay, so we want byte. So what I should do, get a pen and write this down what we want. Let's just go back. So we said we want byte 1. We want byte 1. We want byte 2. 3 and 4 we don't care about. Byte 5. Byte 5, do we really want it? Yeah, it's going to tell us at once. Okay, so byte 5 we will give it byte 6. Don't care about. I don't care about 6. Don't care about 7. Don't care about 8. I don't care about 9 and 10. We don't read any of the analogs. 11 and 12. There's 12. 9 and 10 transmit first feed current in copy net. Okay. Okay, well, we're not wiring any. So, don't care about 9 and 10. 11 and 12. Fork. Again, we're not installing. Okay. 13, we don't care. Do we? No, I don't care about anything there because I'm not wiring half of that in. 14, okay. 15. About point 16. Incorrect direction of rotation. No, don't care about that because to commission it, we would set the phasing up, drive it locally, see that it's opening the right way, closing the right way, and if it's not doing that, you swap at phase, three-phase. No, because you have to commission it manually. About 16. 17. Warning signals are infinite, blah blah. If QM fails, safe, fault. Fork warning closed. Fork warning open. When it was traveling in the closed direction, the fork exceeded, or in open direction, the fork again is exceeded. Do I care about it? No. First of all, I'm not wiring. I don't care about sulfur because we're not using it. Warning, no reaction. I don't care about that because I don't care about any of this because we would be doing this in PLC. And the torque I don't care about because this is water that it's closing on. Actuator is more than oversized. No, I care about torque. 18. Oh, the temperature within the control housing. No, we should never. The external DC voltage, not giving it extra. RC button, RTC button. I don't. Real-time clock is not. I don't care about that. Warnings 3. Fiber optic cable budget. Well, we're not using. Okay. We don't care about that. Log input 2, analog input 1, no. Internal warning, no. Warning on time starts, warning on time running. Operation time warning, I don't care about. 20. Set point position, well, we're not giving it a set. Partial valve stroke test. Because you do all these things manually. No, no, no. 21 and 22 is analog input 2. We don't care about it because we don't have any analog input. 24, maintenance required. I don't think these oaks would follow a more recommendation. 7. Mechanic maintenance required. Seal maintenance required. Lubricant maintenance. Contactor maintenance required. Fit maintenance. I will take by 24. That's it. Not going to do anything with it. By 25. And I don't care about any deactive. 26. Out. Version 2. We don't have anything. We don't have external all these. Build time clock. Don't care about time knots. By 26 we don't want. By 27. Fiber optic. Analog input 1, 2, internal 1. Okay, no set point, no partial valve. So test fiber optic. failure, no, failed stroke to support, fault, no. 29, about local stop. This is in the middle of nowhere. Get this position local. I want to know that. And we'll active emergency stop. We don't have partial valve stroke. Not going to put by 3, by 30 and 31. And so reserved for further function. Check 30. We don't care about that. 31 status of the field bus. Channel 1 active channel. 1 dot exchange. 2 dot exchange. Channel 1 activity. I don't care about it. Get any data back from it. I don't need it to tell me that it's not. Causes of maintenance. The soul signal. Safe ESD, safe stop. Okay, we're not using safety credit level on this. Not built in safety. This 1509. Not using that. Is not people. It's not going to danger factory or anything. The requirement. So 33 to 40. That takes care of all of us. 40. So we only want summary byte 1, byte 2, byte 5, 15, and 24. I like these. Output data, we're not going to worry about that now. So let's yeah. So what I'm going to do is go back. That we want byte 1. I go to our block, and we're going to have to build these decorations. So before we build the decorations, I add a row. We want to be able to switch this thing to auto. Write some logic for that. Going to be full. We want to switch it to manual. We want to open it. We want to close it. What else would we want? That's a word. 1, 2. Just going to put spare 1. You'll see why I'm doing spare 2, spare 3, spare 4. If we go to our block here, there's our DB. Notice 0, 2, 4, 6. B data was sitting 12. Build this update block call. Fine. We go and open that D. Notice 0, 2, 6, so it's 8.0, 1, 2, 4, 5, 6, 7. I might want to do is put interlocks here, and I'll see in 7 or 8. Good. 3, 4, 5, 6, and take one of these spares. Remember, we want to be a local remote, so call it remote, save it. And we need to start building output. Output. E, one. You don't have to. I'm building the right data. So we said we want byte 1. Okay, so EP open, full, E closed, 1, set point position. I don't really care about it, but we make this consistent, and why are we doing that? See point. Ready, note, run, open, run, close, on, alt, alt. Those are the warning and comment here. The declarations is byte 7, alt, byte 60. And so if we've done this right, we should alt our first byte, byte 1, byte 2, want thermal alt, phase alt, select a switch, mode, select a switch, local, limit switch open, switch closed, torque, switch open, torque, That should be the same. Yeah, 1, 4, 5. That takes care of byte 2. 1 byte 5. We want byte 5. There's a fault. It's going to 15 and 16. There's a warning that returns to 17, 20. Not ready remote. Well, we know it's not ready remote because the previous byte we have the selector switches in remote. Selector switch local. Maintenance required. Out of spec. Function check failure. Bicep. Only really want 1 bit out of it. Getting it anyway, so byte 5. Not ready. But warning. Call it 0, 0. So 1 fault. So 1. At fault 1. And wired. Out of deck. Unwired. Byted controllers. Function deck. For failure device. Okay. That takes care of byte 5. We want byte 50. 50. Oh, config. Mains. Fuel quality. Thermal fault. Phase fault. Phase. For that. 0. Oh. One. Fork. L. And fork. L. Closed. Kernel. Warning. Configure. Perfect. byte 15, byte 24. Okay, so we've got a maintenance required for mechanics, got a maintenance seals, got a maintenance lubricant, we've got a maintenance contact, we've got the maintenance civil, and then 5, 6, 7, we've got 3, 6, 4, byte, 4, 5, byte, 6. So you know exactly why we do 7. Notice by filling in these spheres and making it consistent, I filled up the whole byte to become important, so you know. Come on. Date. Enter. So if we come back, see our read data is moved over to 20. Okay. So here we have to set our offset to 20. I'm going to call this one read data. Now what we could do, we could load a pointer, read data, load that into address register. We could load the data instance byte of read data of R1 date that we got it into R1, P hash 0.0. So the first byte was byte 0. They're calling byte 1. That, and we can transfer it to data instance byte is our read data start 10.0. And just like that. So it will take first byte 1 or whatever that we already got in our block that put it here and put it there. Going to take that read data, load the first byte, and put it in our first group of 8. First group of 8 is 1, 2, 3, 4, 5, 6, 7, 8. If I didn't put the spares in later on or whatever, then I would have to go and do this for each bit. I would have to go something like this. And data instance bit of AR1 from a P hash 0.0, so the first bit equals DIX 10.0. I'm going to have to keep up here because now I'm going to have to keep thinking, and I can open myself up here because now I have to go to 0.1. That's just going to become tedious. And 0.2, 2, 3, 3, 4, 4, 4, and so on. And it might be that I've skipped bits in my output, so now I might need to skip 3, 4, 5 and keep track of what I'm doing with that scratch pad. Rather easier just to fill up the empty byte like we did with spares or whatever, just transfer the whole byte in. So we said we wanted byte 1, and here we want byte 2, so we can offset it. So we're gonna, because remember on our side we start with 0, so 1 is actually 2, and that's going to go to 11. So our declarations are consistent. So we've done byte 1, we've done byte 2. We want byte 5, 4, and we're going to go to 12. Don't agree with me? We want byte 5. And byte 5, look at our declaration, will go 12. Not ready for remote. So it's much easier to keep track of what you're doing here, like this. 4 to 12, that was byte 5, and we want byte 15. Our side will be 14. That's going to go to 13. And we want byte 24. Twenty-four, 13. Yeah. What am I missing? 1, 2, 5, 54. 1, 2, 5, 50. Go to 14. 14 being our last byte. See how easy it is to make like rather do it like this. Could go one step further and what we can do is load a pointer to that dot instance byte. Yes. So we could load a pointer to this data instance byte instead of mentioning it like that. So we could load a pointer to okay, see open. And then swap the registers. Let's see if we do that. So we've got that dot in. We've got here we've gone and got this data. ALAR1 B hash C open hash E open E open. What is it? PAR. Change the want to change the password. Example is useless. Oh, I don't remember what the command was. Ah, come on. Oh man, Craig. What? I'm getting old. Oh, heck. Might be tech. Transfer. Got in find. Yeah, one. Might be tech or might be it's tech. I can't remember the it is tech. One have got this in accumulator one. Now we put this in accumulator. You have to swap it around. That's back in transfer there. Good. So that would take care of if we mess our declarations. So all we have to do under each one now, EP open one, yeah. Here EP open was 10, 11 will be term fault 0, 0. Come on, come back. We don't have to change the offset because it will just add the next 8 bits. Term fault 0, 0. Okay. Term fault 0, 0. We'll go. Fault is not ready remote. ready remote. $30 figure. And our last one. Maintenance mechanical. Now we don't care about anything that changes. Or do care if he goes and puts stuff in here and breaks up our byte stuff. But we don't care if he adds another 7 bytes somewhere in between, 7 bits in whatever he adds in between, as long as he keeps it consistent. That doesn't break our telegram, because then we will go look at the first instruction. We will take the first byte quantity, in other words, byte 1 from their telegram out of here. We will load a pointer to here to each open, swap the two accumulators around, then we transfer that first byte that we got here to here. 1, 2, 3, 4, 5, 6, 7, 8. First byte, those 8 bits. And that makes our life much, much easier. And that takes care of all our read data. So I'm going to cut it there in our so cut. Got our read data, get our logical address, actually get the data from the device, read data transfer to block data outputs. What tomorrow we will do is nodes and the locks. Obviously, we want to be able to switch this device auto, manual, local, remote, and we have to have the same sort of functionality within our software to say, hang on, if this thing's in local, what applies to the PLC interlocks apply to it or not? It doesn't help us giving the thing a stop on the PLC if it's being driven locally. So we use that internally as well. We mimic what the hardware is doing. Unfortunately, I don't have a PLC and a valve to test this on, but we will be able to check it in one of the episodes, because when they build my panels and the equipment is delivered at the end of this, then we will actually hook this up to this PLC and the HMI that's coming, and we will drive the devices and parameterize them and set them up, and obviously check that all our code is working. While we edit, let us just check what do we want from the output bytes. So that was in output data. In controller can control it like Okay, to perform remote operations, the switch must perform. That's something that you switch locally on the device. That, because it's out in the middle of nowhere, it always stay on remote. Okay, commands. Byte 1. Field bus open. Give it an open command, a close command. We want byte 1. Field bus set point, run to set point. Well, we're not going to be giving boys zero, we'll force that. Field bus reset, yes, we want to be able to reset the thing. So we remember those spares that we added in here. Those spares, reset. Oh, I didn't. The spares that we had, I just went a reset one of the spares. The rest we don't use. Okay, so we'll spares in there. Byte 2 field bus set point. Bring it a set point byte 3 and 4. We're not going to be using 3 and 4, so we still use byte 1, byte 5. We have to enable local. Able to open, able to close. We're not going to set change service to emergency zone. About the partial valve stroke test. I think we might need to send these enable control. If he unplugs the bus, then thanks, because we'd be getting a 0 via the telegram, and then we can't do anything. You understand what I'm saying? So if we give it a 1, so it's coming via the bus. Actuator operation via local controls is enabled. So it should got the bus plugged in, and we're telling, okay, you can operate in local, and he switches it to local. Now you can drive it. How we unplug the bus, now it's still in local and you can't drive it. Makes no sense. Right? There's a problem. Either there's a big problem with their control, or there's a problem with their wording. I'm going to add byte 5 as well, just in case. Byte 1, byte 5. 6 we don't care about. We're not going to be running positions. Blah, 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 blah. It's 7 digital output. Well, I'm not going to be driving any digital output. Not wired any. Fine for that. Byte 8 digital outputs definitely haven't designed anything there. Byte 9 and 10 process value. We won't be sending it the actual process value. Remember, we're using this as a valve, not by a special module for this valve. It can have its own standalone PID control in the valve. I don't like signing like that. I understand sometimes you a critical thing if you lost your whatever this thing control on its own. I don't like it. Don't have the requirement for the standalone on-off valve. Well, on-off valve, not doing any process, not modulate. Open, close, or it'll be in a position of travel. Not going to be hovering around 50, 55, 50, 55 to try and control process bit. Okay, so 9 and 10 we don't care about. 11 and 12 don't care about sending an analog value to the actuator. not wiring the analog. 13 and 14, we're not, again, we don't use the output. 15 to 16, reserved. Then we're done. Property services is like data. Care about a site data. What is the a site data? They're talking about device identification, especially. Not like that. I don't care about the serial number of the. Care about the manufacturer's identity number. I don't care. What do I care about any of that for? Acyclic data in this case, I don't want. Don't be quick to write acyclic data off. Some devices, especially the property bus, to get special diagnostic data in case of a fault. So you don't want to always be following the diagnostic data of this thing if the thing is operating normally. But in the case of a fault, then you might want to go acyclic. In other words, once off, please give me the diagnostic data in your buffer. Great, now I can transfer operator like this. Okay, redundancy. Here they talk about the different topologies of connecting this your PLC. So you have it in a ring. So if you break a leg, communications will carry on. But they talk. We are not. In this case, we are not. In our case, we're not connecting anything in a ring. Topology. It will start because of the switch I bought. Because if you switch the power to this thing off, it loses its mains and it can fall. Well, it can't switch any. It helps us fuck all if you do devices. So what we do, because I don't have that many devices in the field per network port, I take 6 copper ports on my controller side. 1 there, 1 to there, 1. I don't care about the, and they go on and give you a whole bunch of rubbish, troubleshoot. Anyway, I think that takes care of today. Was what am I doing? Okay. I'm getting used to this. What we can see, we can use system functions, get logical address of the device, that address there. We can use system function again once we've got that logical address, get all 34 bytes of data, all that data that's thing there. Get all that data that's sitting there without us having to type millions of it. We can put it in our scratchpad. The words are scratchpad up here. And then we can selectively take out of that scratchpad. If we design our declarations properly, with very minimal fuss, we can take that scratchpad data, data, and populate our declarations, our output declarations, because this is input data from the output on the function. Okay, if that makes sense. With very minimal code, we have gone and got 1, 2, 8, 1, 2, 3, 4, 5 bytes of data. With very minimal code, 40 signals, roughly. 5 times 8, 40. With a very minimal bit of code, we've gone and got 40 signals, and now, as long as we keep our block interface consistent, as long as we know that's there, we can add 7 bits before this, we can add 7 bits in it, as long as we don't interfere with the byte that's there. So we can add another byte anywhere in this, and our code, we don't have to go and change. And that's what we really try. So as always, I hope you enjoyed this. Made me think a bit. I'm a lazy programmer, and less code I have to write, the less I have to check old file. Just out of, well, I needed to get some stuff this morning, so our news, well, websites and whatever, I don't think updated properly or whatever, because local shop says they will be open at 7 a.m. in the morning, and I popped in at 7 and I sat in the parking lot at 8. Not a problem, I see. Honestly, catching up on Twitter and whatever. And eventually I got a shopping center. Oh no, and the utter stupidity. Come in and they've got trolleys and they're rushing up and down the aisles and leaving the thing in the middle of the aisle, so you have to fucking wait for them to get past them or whatever. And even then with the panic buyer, one Tani was going, like, she must have taken the whole shelf of baked beans. Look, I love baked beans and toast, but fuck me, there's no ways I'm buying a supermarket shopping shelf full of baked beans. For what? I mean, the craziness of, luckily the things I wanted, I went specifically to Spar because I'm avoiding chemists, because I think that's where you're going to get a lot of sick people. I wanted a vitamin supplement. I wanted a vitamin C stuff as well. Shaving cream. I thought I'd get extra cat food. Oh, and I wanted chocolate. Not the necessities, but the necessities that I did need to get. I needed to get bread. I needed to get. There was some bread. But watching the chaos of people. I mean, sure, ideally stay home, but I mean, you can't freeze 10 loaves of fucking bread. You can't. Oh, I needed eggs and milk. Other than that, well, remember, we're not allowed to buy booze in South Africa. We're not allowed to buy cigarettes. But I think they're going to have to lift that some later, because after 21 days you can buy it. But the utter stupidity of the things that people are stocking up on. It's not like you're getting fucking people buying cans of tuna fish, mate. Cans of baked beans, I really. But anyway, it is what it is. I hope you enjoyed part 2 of this. If you find it useful, if you've got comments, you've got questions on this. I know this is not stuff they're going to teach PLC course, but it's why I write in statement listening, because it makes my life easier. Yes, I will go ahead and comment this, and what I will do in the block interface, as they call it, I put here byte 17 and 20 in the comments. What I will do is go for each of these declarations, I will go and put in something like a high equals at this state, low equals this state, so that the comments are full. We really don't have much more left to write in this block. We have to write a few things for the input data, so that we can get basically our input declarations, that we can drive this valve, and basically the interlocking. The interlocking is very simple. Either all 7 of those interlocks are healthy. So, an example, there is, let us do let's do that. Load pointer to brewery. Such a color today. This new computer my work gave me, because you need quite a hefty thing to run your machine on. And they've given me this fancy MSI gaming thing. Keys light up, but the way that the keys are laid out, it's just horrible. I mean, it's a poker machine, don't get me wrong. Yeah. So we want to load input byte of AR1. Input byte of AR1 from a P hash 0.0. So we want to load the whole byte starting from there. So load W hash FF. Right. Doesn't it like FF? I sent load FF, in other words, each one of those F's is a nibble, 4 bits. As long as all of them are high, I can either do it like this, equal to I, or I could say not equal to I equals close if we click close. Don't have a close command yet. Going to have it. And simply put, if any of these 8 bits are low, close the bell. So that's interlocks, but obviously there's a bit more to it. We want them fail safe, so we try to be a bit more to it, but we'll cover that tomorrow's lesson. Anyway, as always, I hope you enjoyed it. I hope you hope you stay safe, and I hope you healthy. Enjoy this time of solitude. Catch you in tomorrow's lesson. Till then, take care.